Hi, my name is Stephen Burkot, and you're watching my Physics Extra Credit Report. So, basically I'm going to run through all of the math and algebra here and the analytical stuff, and then I'm going to go and show my VLab. So, in the first problem, it asks us to find the speed that it's flying, and for here I used an energy principle because it was a lot easier, and I based it off the video and using the heights they gave. So I just set the initial gravity is equal to the K final plus the gravitational final plus the spring potential. And some of the other things I had to use was the K, which we solved by using the mass divided by the stretch that they gave us. And then we worked through all of that, and we find that the velocity is equal to 20.4. You can look more into my work if you really want to. This is actually problem number 3, so I'm just go down to problem 2. In problem 2, it asked to find the tension when the force was ideal, when the string was ideal. So for that, I use force tension is equal to the centrifugal force plus the force of gravity, which is basically kind of a pendulum idea of how you measure force of tension. So we use for centrifugal force, we use mv squared over r, and then add simple mass of gravity because it's straight down at the bottom. So there's no component, it's not split into components. For that, I got 2,162.7 newtons for the force of tension. Now for the third one, it asks for find both the velocity when it's 30 degrees in the bottom and the force of tension. I actually held off on the force of tension here because it's more relevant later. I once again used a energy principle because to me it was simpler. First I found the height off the ground it was by using this triangle where it's 30 and 60, and then I solved for y, and then I subtracted from the overall height, which is 150, minus what I found for y, 11.41 meters. Plugged all this into the energy principle, solved it out, I got 25.93 meters per second for the speed at that. Moving on to problem 4, once again it asks for the force of tension at, estimate the stretch. For this I used the force of tension I found, and then I did the force of spring plus force of gravity when it's at the bottom, so it doesn't split into components, and so I subtract that and I divide by 225 and I get 3.048 meter stretch. Now problem 5 is where it all kind of comes together, and what happens is I come and find the force of tension from earlier, so I use F grad plus FC for stretch, and I get 639. But this is at the bottom where it comes all together, so the full force of tension is equal to the spring force plus the force of gravity plus the centrifugal force. I do all that, and then I find the stretch at that point is equal to 1.689 meters. And here's my VLab. Hi, this is my VLab. As you can see, I just basically took a spring code and I modified it to go with the demonstration in the video. So now I'm going to run it. As you can see, it appears as the weight goes down, it drops. The arrows in the system, the green one is the tangential force, the blue one is the perpendicular force, and the blue one is the total and the yellow one is the perpendicular. The reason the yellow one is acting a little weird right now is because the way a spring works is it's compressing slightly at the top, so it appears that it flips around, but in reality it doesn't. This is a slight issue with using a spring model, and especially in VLab where everything acts like it's very precise, not exactly how it would in the real world. The jumper, when he first leaves and travels down, he would have the greatest speed when he hits the bottom. You know this basically through an energy principle because all of the potential gravitational energy is turned into kinetic energy, which he would have the least gravitational, so the most kinetic near the bottom. This would also be where the tension is greatest because the force of gravity is acting straight down on it, which means the rope would have to work to go against it. This is the basic of my VLab presentation. I will now show how it looks in an ideal situation. Hey, so here now is my VLab where it is an ideal, so there is no stretch. Essentially it just looks like a pendulum. Nothing too crazy, as you can still see the arrows point tangentially and perpendicular, and the blue one is the total.